So here's something that looks really complicated. This is how physicists see waves. Let me walk you through it. It's not very complicated. So this formula on the left side, all it's saying is that the displacement of the string is a function of the position and the time. So the left-hand side of this equation is saying that the displacement of the string, which basically means is how far the string is away from the equilibrium point, is given as a function of x and time. If this is t, is how far away it is along the x-axis and time, given by the amplitude, which was the height of the wave, times sine of kx minus omega t, where a is the amplitude, x is the position of the string along the x-axis, t is the time, and omega is the angular frequency. In general, this wave, which is a positive x, is a wave traveling in the positive x direction. So this is a wave traveling in the positive x direction. In textbooks, this y will also sometimes be written as this fancy looking psi. All that means is it is the displacement of the string away from its equilibrium point. That's all that means. So I'm going to read it one more time. So starting from the left. Everybody ready? Watch the screen. Y as a function of x and t equals the amplitude times the sine of kx plus omega t, where omega is the angular frequency, t is the time, x is the position along the x direction, and k, which is the important thing, is called the wave number, defined as 2 pi over lambda, where lambda is the wavelength, the length of the wave. Okay, so now I'm going to ask you a question. If this wave is given, what is the difference between this wave and the one you saw here? Do you see a difference? So this was y equals a. So the previous wave was this one. What's the difference between this and this? Aha, what does that mean? So k cannot be negative, but x can be. So when I said about this wave, what direction was this wave going? So what is the difference between this wave and the other wave? That's it. So this wave is going in the negative x direction. So this wave goes that way. This wave will go that way. So this wave goes to the right, and this wave goes to the left. That's the only difference between these two. Now I'm going to give you this. And I'm going to ask you, a transverse wave traveling along the string in the x direction has a form of this scary looking thing. What is the amplitude, angular frequency, wave number, and period of this wave? What I want you to do, if you get a question like this, I want you to write it as this. And then I want you to write what we saw before. And I want you to make a one-to-one correlation between the two. Do you see it? Do you see it? Do you see it? Now let's discuss the questions that they're asking. So number one, it asks me for amplitude. I know my amplitude is A equals, somebody said 3? Yes. Number B, angular frequency. And what did we say angular frequency symbol was? Omega. Do you see omega? The correlation? What would it be? 2 radians per second. Number C, frequency. What's frequency? I know, I'm looking for frequency, but I know omega equals 2 pi f. So frequency will just be omega divided by 2 pi. So that means frequency will be what? 2 divided by 2 pi. Somebody do that math. It'll be like 2 divided by 6.3 something. Hertz. Yay. Okay, number D, wave number, K, here it is, yay, 72, and just put the units there. I picked up from here. And last but not least, the period. And I define the period as 1 over T, which means period will just be 1 over F. And my frequency was 0.32. So my period will be, somebody invert that and tell me. 3 point what? 125. Done. And that is how physicists see the world in terms of waves. This is what a wave looks like to us in math. Okay, everybody got that?